thank you for organizing this event and for inviting me. And thank you all for coming to this talk. I'm really excited to see you all, a lot of colleagues and friends and co-authors. So it's really fun to see you. And I hope to have a good interactive session. So please, if you have questions or comments, then feel free to speak up or raise your hand and speak up. Okay, so what I want to do today is kind of cover this one of the advances that happened in the last few years, which is around this Simplex protocol, and talk about Simplex and its many different variants. So in particular, here's some of the things that are related to Simplex. Some of these are kind of protocols or papers that are published, and some of these are topics that I will talk about in this talk. And really, what I want to kind of highlight here is that, at least for me, Simplex is kind of a protocol that allows at least me to coalesce multiple different approaches for consensus. And it's actually nice to see how these different approaches can be viewed through this angle. Okay, and I really want to kind of thank a lot of people for this talk. A lot of my colleagues and co-authors, and I'm probably missing some of them here. And as usual, all these good ideas are from them, and the mistakes of this talk are mine, of course. Yeah, really, like most of the things I'm going to say here are kind of known, right? I'm not trying to give you anything completely new in this talk. Okay, and Tim and I didn't coordinate anything, but I'm going to say something very similar, which is kind of why I really love consensus. Again, if you look at computer science, there's very few areas where there's such a nice connection between beautiful theory and kind of impactful practice. And this, to me, is kind of really a fascinating area to do research in, because it's not only kind of interesting from a theory perspective and not only kind of impactful in the real world, but it's also kind of the interaction between these two things give new ideas. And I really want to highlight the fact that this is a two-way street. So some people say, oh, you have really good theory ideas, and then they get translated into, technology transferred into practice. And actually, what I find is that the most interesting things are actually both of these interactions. So sometimes there are really good ideas that happen in practice, and then you try to understand why they work or why they don't, and that kind of gives you new theoretical insights. So really, for me, these kind of back and forth is the important one. Again, from a theoretical perspective, what I like about consensus is that, much like other foundational problems, these are problems where it's very easy to define the problem, and then solving it is kind of something that we are still doing over and over again. I have this funny story. I don't have the quotes here, but every 10 years there's somebody that says, well, consensus is done. There's no more things to solve about it. It's completely solved. And usually when they say this, I actually look at their arguments and they make a lot of sense, right? So it's like, okay, there's nothing more to do. And then I kind of just smile, embarrassed, say, well, I'll just continue thinking about some of these problems. And then it turns up that there's new things to do. So I don't know, maybe after 50 years, that's it. There is no more 10 years of consensus. But at least the history has shown us that every time somebody kind of predicted that this is the end, there are more interesting things to do. So yeah, I hope this is the case as it will continue. And again, this is for me an indication of kind of a good foundational mathematical object, right? So just like other things that kind of continue to have good problems. And of course, in practice, we're seeing consensus come up in many, many places, right? So obviously, any cloud infrastructure that you're using today, the backbone of the fault tolerance is kind of using consensus protocols. Blockchains, which is kind of the reason that we're here today, again, the backbone of that is again the consensus protocol. And I guess when I'm looking forward to anything that will have to provide trust, anything that will have to provide kind of a way to govern things that will need to be resistant to failures, then consensus is going to be the only approach going forward. If I had to predict what will be the interesting things in the future, I would like to say, multi-party computation is like an enhancement of what blockchains give us today. And if you think about that, from a cryptographic perspective, you have things like FHE, right, fully homomorphic encryption, which kind of basically minimize MPC to a lot of cryptography and consensus. So even MPC at the end of the day is going to be cryptography and consensus built into it. So I see a long future for this, and this is kind of why I love this topic, and I hope you will continue loving it as well. Okay, here's kind of a brief and a subjective history of blockchain consensus. I don't mean to offend anybody. I've definitely missed a lot of trends and things. So if you're looking at this and say, oh, I don't see my work and so on, then please accept my apologies. I really kind of just want to make a caricature to make a point, and so by doing that, I'm kind of simplifying things a lot. But really, kind of the first, I guess, era was the pre-blockchain era, and this is kind of highlighted by PBFT. I think this is an amazing project. And in addition to that, kind of this kind of core understanding of separation of consensus and execution. I think that's kind of a very important paradigm for state machine replication. Again, these are things that have been done in the late 90s and early 2000s, but extended a lot. The next stage, obviously, is this Bitcoin disruption, right? That kind of came upon us in the world. You'll hear a lot about it later today. But I'll say just kind of two high-level things. One is this amazing property of Bitcoin consensus, Nakamoto consensus, that it is very, very trust minimized. So it does not need a PKI setup to start working, and that's kind of an amazing thing. And the other thing is this idea that you have rotating leaders in order to kind of get paid every time you're proposing a value. And this kind of chain quality idea of rotating leaders is maybe a major differentiating factor between, I guess, Nakamoto consensus and previous BFT consensus protocols that kind of use this idea that we'll have a fixed leader that will propose all the time, and we'll only replace this leader if some extreme event happens. Okay, then kind of came these first generation consensus protocols, and I think we'll hear more about some of them and some of the new advances in them in later talks. And I guess, at least the way I think about this, they were basically trying to kind of take the PBFT idea and combine it with this idea that we want to have rotating leaders to get chain quality, and to do this in an efficient way. And mostly succeeded, but then kind of came these additional needs, and in particular, the first need that was clear was getting higher throughput. And so this is maybe these second generation protocols. And I would highlight here these DAG-based protocols as kind of the canonical example. But there are others that try to kind of push better throughput into consensus protocols. And part of this is really this idea of separating data availability from consensus. Just like separating consensus from execution is extremely important, separating data availability from consensus is extremely important, because then you can use techniques like error correction code to kind of push high bandwidth data availability. By the way, I realize that you're very silent. So if you have some comments or things you want to say, then please do.
And the other thing I'll say is, if you do want to ask a question, please, we have a couple of handheld mics so that your questions get archived on the recordings that go out to posterity after the shot. So please wait for someone to bring you a handheld one.
You have one, and where's the other?
The other one's right there.
Yeah. Okay, good. Yeah, Roger, you have a question. No?
No.
Oh, okay.
I just wanted to point out mine.
Okay. Good. So everything is good. No questions? So yeah. So I guess this is kind of this second generation that was trying to focus on high throughput. And then okay, that means you have a lot of transactions per second, which is good. But then the next measure that people were kind of interested in is, well, now that we have a lot of transactions per second, we want the latency of these transactions to be small. So we want to kind of reduce latency, not just get high throughput. Right? In theory, getting just high throughput is kind of easy, right? Because you can run consensus, let's say, every 24 hours. Right? So you can just push all the transactions, and every 24 hours you can kind of run one consensus protocol, and then you get very good throughput. So really, the challenge in consensus protocols, and if you ever implemented one, is kind of getting this trade-off between both high throughput and low latency. And I would say kind of one of the nice things about these third generation protocols is the focus on low latency. So again, it's not that these previous protocols didn't focus on them, but I guess this is kind of the hallmark of Simplex, that is trying to optimize for low latency, both in the good case. That means that if there's a good proposer that's trying to commit, and also in the case that this view is kind of not succeeding, maybe because of asynchrony or because of some sort of malicious behavior. And in that case, we want to at least make sure that we're replacing this leader in a relatively fast manner. Okay, we don't want a malfunctioning leader or a malicious leader to kind of cause us to delay the consensus protocol for a very long time. So this is kind of these simplex protocols, and will be kind of the core of what I'll talk about. And again, this is my prediction for the next wave of things. And again, these generations are intertwined, so don't think about them as a complete partition, right? These are kind of intertwined waves. It's kind of focusing not just on the performance side, on the throughput and latency, but also trying to focus on different and new and more stronger validity properties. And in these validity properties, I want to kind of put a large bag of properties. So censorship resistance is one. So if a client has a transaction, you want it to be committed quickly and not kind of be able to be delayed for multiple blocks. We'll talk about notions of hiding the transaction in the mempool. I think you'll hear about that later in this week. And other notions of how do we prevent the bivalency advantage of the proposer from kind of taking advantage of that and getting some sort of economic benefit from the fact that proposers have bivalency. Okay, any questions about this slide or anything that you think I kind of missed? Yes?
Could you say something about the motivation?
Perhaps if you
So, could you just say something about the motivations for the shifts in focus? Like, were the shifts in focus because the prior generations were very successful at what they were trying to achieve, or maybe because they were very unsuccessful, or because I can imagine many different reasons why people suddenly start exploring different objectives.
Yeah. Good. So first of all, this looks like a linear scale. It's not completely linear, but I will say, if you've ever kind of tried to implement these systems, you kind of work through bottlenecks, right? So your system works, and then you say, oh, what's my problem now? Well, my throughput is small. Okay, so now the whole focus is about let's fix throughput. Okay, you fix this throughput. Now you say, well, now I have this wonderful throughput, but now you have a new bottleneck, which is your latency. So you go and fix the latency, and then you say, well, I have this system that has wonderful throughput and very low latency, but it doesn't have censorship resistance, right? So actually the actual latency that a client sees might be much larger. So I guess my point is, this is my hypothesis, that basically people had systems that were built, and then they looked at the first bottleneck that they saw, and they tried to fix that, right? And then once that was fixed, then another one. But yeah, maybe it's a bit of naive. Maybe somebody has a better answer to that.
But so just so I can clarify for understanding, it does sound like you're saying these were relatively successful at the objectives they were trying to.
I think so. Yeah. Yes. Oh yeah, good. Yeah, I see your point. Yeah. So definitely, I would say this idea of separating data availability from consensus is kind of the core reason for high throughput. The reason, maybe I should have said this more clearly. The reason is because consensus typically is done on one digest. Right? One small cryptographic digest. So consensus should never be a throughput bottleneck. If this small digest includes 10,000 transactions, right, then you can get much higher throughput. So in a sense, kind of, by getting very efficient data availability, you can have a data availability certificate and basically reach consensus only on this data availability certificate. So I think that idea was very crucial for getting high throughput. And yeah, so I do think we are getting now very high throughput, right? To the extent that, the way I like to think about this is what is the slowdown relative to a system that would just run one server that's executing these transactions. Okay, and ideally what you want to do is get the throughput bottleneck to be your execution bottleneck. Okay, so if you have a lot of transactions, and if you run it on one machine, then you want to be throughput bottlenecked by the execution of that machine. Okay? Then you can try to improve execution, right? To parallelize it and so on. And so roughly speaking, you should try to aim for a consensus protocol that gives you a 10% slowdown relative to just one machine. And I think we're kind of there. Okay, kind of best. That's high level with that. In terms of latency, we'll talk about this in this talk. There are lower bounds about what is the best you can get for latency. And I think there's interesting theory questions here, but we're getting very close to that. I think this fourth wave is still kind of in flux, and people are still trying different approaches. Any more? Anything missing here? Yeah.
Can I ask a question? Is it like in the third generation, does it also like guarantee high throughput as well?
Yeah, I mean, to the extent that you are kind of doing this separation, I think it typically does, yes. Yeah. Yeah. So the one thing that I think is missing here is kind of these Algorand approaches of subsampling committees. So I think that's kind of actually an important avenue. So I didn't mention it here, but I think it might reappear maybe maybe later on in this. There was another question? Okay. Yeah, Roger.
I don't have a mic. It's all true, of course. I would say that it's not that the first generation protocols stopped at the first generation. No. They look also at the fourth generation. So sort of like what you mean by generation is here the new idea they introduced. But I think when you look at systems, actual build systems, then I'm sure Alberto would say, but we're also looking at generation 3 and 4.
Yeah, you're right. You know, in hindsight, I think generation is the wrong word. And I think when I talked, I used the word wave. So these are like waves of ideas. And I think, yeah, your systems will have like all these waves, right? You'll have low latency, you'll have high throughput, you'll have a rotating leader. Yeah, so I absolutely agree with you.
I'm wondering if it shouldn't be a pyramid rather than a list, in the sense that the later waves, let's say, or generations, usually leverage the inside of the former, right?
Yes.
Like you could have Simplex using the separation of data availability consensus if you like, and I'm pretty sure that Joachim accountability would work nicely over Simplex or anything above it, right?
That's a really good point. Yeah, I think that strengthens what Roger is saying. Yeah, so I think these are like built one on top of the other. Yeah, so so please think about this as kind of compounding waves, and not throwing away the old, right? If that was the. Okay, so this slide is hopefully not necessary for most of you, but I just want, since we're going to talk about consensus a lot, then at least I want everybody to like be on the same page about what that means. In particular, what I will be talking about in the next half an hour, at least 45 minutes. So I'm picking a very specific version of consensus, but basically consensus is 3 properties. Right? And these properties are liveness, which means that something good needs to eventually happen, safety, which means that bad things never happen, and validity, which kind of means that if something good happens, we want it to have some nice property. Okay, and so specifically, in this version, liveness will mean that everybody eventually holds a certificate of a commit. This is maybe different than other types of livenesses where you just want to say that you know what the decision is. Here you actually want to have a certificate that you can show other people. So this is what I would call a provable consensus protocol. And I think for blockchains and state machine replications, this is really critical. Okay, the second thing is that if you have 2 valid, yes?
May I ask why it's validity of
Can you press the mic back?
just the validity part, so client, who is the client?
Yeah, good. So
Client who is the
perfect. Yeah. So you see this. I'm happy that I put this slide up because I want to, I'll clarify even more. So we have a bunch of servers, and these servers, validators, are trying to implement a state machine replication, and there are clients that are talking to this machine. So basically, I'm hiding the clients here. I'm not going to talk about censorship resistance. I'm not going to talk about the mempool, right? So basically, I'm just assuming that servers start with some valid client input. So that's kind of saying that I'm abstracting away a mempool, and these servers already have some client input.
But they are considered the consensus as proposed. It's not a block of several transactions.
Good. So this is kind of this comment here. This is a single shot consensus. So basically, in your mind, you should imagine that what we're doing here is we're reaching agreement on block number 1, and then reaching agreement on block number 2, and then block number 3. I will show you. The client provides the inputs, right? And then this block will contain a bunch of client commands, or just one client command, right? Just for simplicity. So I'm going to really abstract away consensus, right? And focus on the core single shot version of it. I'm going to focus on a provable version of it, so you have a certificate. And I want it to be externally valid in the sense that I want to have a proof that this is really a client command. you'll see that if you can solve this problem, you can basically solve any other problem in consensus. And the reason I'm kind of focusing on this problem is because it really cleans out all the problems of, oh, there's like multiple different blocks, or what if the client sent the message but it didn't arrive, and so on. So I'm kind of abstracting all that away and focusing just on the consensus aspect of it. Any other questions about the problem definition, formulation? Yes?
So in, I don't know whether it's on the slide or whether you just said it, but you said single shot, but on the other hand, in liveness, you have eventually. Does the eventually refer to later later shots, or is it within the single
Oh, yeah.
shot?
So we will. So I think one slide, next slide, hopefully we'll talk about what exactly eventually means in this framework of partial synchrony. But really, I should think about this as a one-shot protocol. And consensus is kind of this strange beast where we don't know how to reach consensus in, let's say, a constant number of rounds, right? So there are lower bounds that show that in asynchrony you might have infinite executions. Even in synchrony, you might have t+1 rounds. So this is kind of this eventually basically is hiding this fact and saying that, yeah, there will be some time where we all have the certificate. I'm not even saying when, right? When we care about the efficiency, the worst case latency will be very explicit, right? And we will be very explicit.
So you do mean within the single shot?
Within the single shot, yeah. But if you want to think about this as kind of a multi-shot, then what this is basically saying that the chain is progressing, right? So every time, every some unit of time, there is some chain progression. Okay, any other questions about the actual problem definition? Good. So now I'm going to kind of remind you about partial synchrony. This is kind of, again, one of the amazing successes of theoretical computer science. Is this middle ground between the asynchronous model of communication, where messages have unbounded delay, so the adversary can decide the delay of any message in any way, as long as it's some finite amount, versus the synchronous model, where there's a delta bound on messages. And partial synchrony is kind of the middle ground. It says, well, up to some point, which is called the global stabilization time, the system is asynchronous, and after that point, the system is synchronous. Again, it's a very strange model in terms that the real world probably doesn't look like that. But the huge success of these protocols is that theoretical protocols that are built for partial synchrony are also implemented in practice, right? So in some sense, this protocol does capture something really good that's happening in practice. So this is kind of the definition we'll use, and later on we'll refine this definition and see there's other variants of it. But really, if you send a message at time t, then it will arrive at the maximum of t and this global stabilization time plus delta. So if you're after GST, messages take t plus delta, just take delta delay. If you're before GST, it might be very, very long until you reach this global stabilization time. Make sense? This should be not new to anybody here, right? Or good.
I like that you mentioned practical systems and partial synchrony. So we are assuming essentially that you have infinite buffers, right?
Infinite?
Buffers. Because everything that arrives before GST should be deleted.
We will talk exactly about this. We will talk exactly about this later on in the talk and see that this is a problem in Simplex and how to deal with that. Yes, you're absolutely right. So as you know, this kind of enforces already a limit to how many Byzantine parties we can handle for consensus, right? So we cannot handle a third or larger. And this is this split brain attack. I assume everybody here saw this. This is not new to anybody. But this is basically this idea that if the adversary controls a third of the parties, then it can kind of copy itself into two copies. One copy says 1, the other copy says 0, and each copy is going to talk to one of the other third of the parties. And in between these honest parties will be delayed by partial synchrony, asynchrony. Okay, and then you can kind of show that you will reach a safety violation. All right. So then kind of the best we can hope for is that the number of parties is at least 3f plus 1, right? Because 3f we cannot. And the kind of the paradigm that again was built going back to Lamport's Paxos protocol, right? And PBFT, and then all these partial synchrony protocols, is kind of getting these two types of properties. So we always want safety, and we want to guarantee liveness after GST. So this goes back to your question about what is eventual. Now I can phrase it a little bit better. It's still not formal, but I will say, some latency after GST. Because GST is kind of an event that has an unbounded time, right? I can't say after 3 rounds. I will say there are techniques to kind of get better liveness than this one, right? The asynchronous protocols, but I guess these are still not used today. Okay, any questions around the partial synchrony? Again, this should be something that everybody knows. Good. So let's now focus on the core of what we're here for this talk, which is Simplex. Why Simplex? Why are we spending our effort on Simplex? So I have 2 reasons, maybe a third one for me. But really, kind of, if you look at the theory paper, it obtained something that previous protocols could not obtain, right? Which is a good worst case latency. So this is kind of, the worst case time that it takes after GST for a bad leader to be removed. And it does that without requiring large messages. Okay, so this is kind of the theoretical advantage of Simplex relative to other protocols. And again, this goes back to these 3rd generation protocols whose goal is to minimize latency. And again, this is kind of this latency minimization result. And then I think maybe more impactful is kind of from a practical perspective, the protocol itself is relatively simple. And engineering simple protocols has a lot of advantages because typically real systems have not just a consensus protocol, right? Nobody cares about consensus. You want to do a lot of other things. And so you're probably going to modify and add things. And it's much easier to kind of reason about modification and changes when you have simple protocols, right? If you've ever maintained a very complicated consensus protocol in your life, you know that that's kind of one of the big pain points. And again, for me, one of the big advantages of this is that it allows me to kind of re-explore all the problems that I looked at in the last years and kind of think about them through the Simplex lens and ask the question, does Simplex kind of make me learn something new in this problem? Sometimes it does, sometimes it doesn't. Okay, so how is Simplex different than other protocols? And I'll try to be later on even more precise to do a comparison. But really, first I want to say that all of these consensus protocols look very similar. And the nuances and the names, sure, they're kind of important for brands and so on. But really, if you kind of squint, they look very similar. Well, they all assume partial synchrony. We said that's kind of the winning model of the day. They all have views, and in this view, there's a fixed leader that is kind of the proposer. And then they move to the next view, and then a new leader, right? Sure, there's a difference in how you choose these leaders and so on. And then they all have this very simple, obvious thing to do, which is they record n-f votes as a certificate. It makes sense, right? Like, you want to say, well, what is there's a proposal, people need to vote for it, and then you want to record kind of the reasonable case of a success, which is that n-f people vote for it. The reason it's n-f is because we assume there's f failures, so the best we can hope for is n-f. And so they all kind of have this certificate property. And Simplex, I would say, has these 3 properties that not all other protocols have. So the one thing that it has is it's a dense protocol. And by dense, I mean that you leave a view with some certificate. So there were previous protocols where sometimes you leave with a certificate and sometimes you leave with nothing. Right? So when you leave with nothing, you don't have anything to show to other people, to prove to other people about what happened in this view. And so by leaving with a certificate in each view, it kind of gives you some sort of record that you can show on each and every view what happened from your perspective. The other thing that it kind of does, and again, this is related to this first bullet, is it looks not only about positive votes, but there's also kind of a negative vote or a vote for bottom, and then kind of will record these kind of n-f votes for bottom as a skip certificate. Okay, so sometimes, for example, in a view where nobody talks, right, at some point, basically we'll have to vote, and the vote is, well, we didn't hear anything. And so if n-f people said we didn't hear anything, we'll call that a skip certificate. And again, that's kind of a property that Simplex has. And then kind of derived from these 2 properties is a third one, which maybe relative to other protocols complicates Simplex, which is that it could be that the view has multiple different certificates. Okay? Not in a view where there's a decision, of course, we'll see that, but it could be that some views have multiple certificates. For example, a value certificate and a certificate for a skip for bottom. Make sense? Any questions? Good. So now we'll kind of just focus on how we're going to describe Simplex. And the way I'm going to do this is by decomposing it into two parts. And what I'll call an inner protocol, which basically just handles what's happening inside a view. And then an outer protocol, which kind of governs how between different views we're kind of reaching a correct voting rule. So we're going to have a voting rule that is kind of across views, and then an internal protocol that works in views. And so now we're just going to focus on the internal Simplex protocol. And it just has these three properties, right? So the first property that we want is that everybody exits with a certificate, right? That's this notion of a dense protocol. So that's kind of the first goal, right? You run this protocol in a constant number of rounds. So now it's going to actually be, in some bounded amount of time, everybody exits with a certificate. So for example, a failure mode will be that, you're not getting a certificate. But obviously, a certificate is kind of forwardable, right? So if I have a certificate, I can send it to other people, and they can use it. OK, the other thing that we want to do is kind of say, well, if we're after global civilization time, so the leader and we have an honest leader, then we kind of reach a decision quickly, right? This is kind of the real thing that we want from these consensus protocols, to reach decisions quickly. And so that's this second validity property that says that not only will we reach a decision, but we'll actually reach a decision in 3 delta time, so in 3 network delays. It turns out, again, 3 is kind of the best we can hope for. Basically, we propose, we vote once, we vote twice, and we get a commit certificate.
What is delta?
Yeah, good. So delta will be the time after GST of a network delay. So if you remember, the capital delta was the maximum delay after global civilization time. So delta will be the actual delay. The actual delay might be less than capital delta. So for example, typically you assume that, I don't know, let's say 100 milliseconds is your capital delta, but maybe if you have a good execution and it takes only 60 milliseconds, then it takes 60 times 3 and not 3 times 200 milliseconds.
So they connect that just to whether a protocol uses timeouts or not. Is it your secret thing about it?
I will say that, so I guess, OK, partial security protocols have timeouts. There is this notion of whether views are starting at exact fixed view schedules or they are kind of changing over time. In both of these cases, it would be nice to actually get a commit certificate in 3 delta. So that's kind of what we want to do in both of these cases. So even if we have views that are every 3 delta, it's fine if we manage to actually get a commit certificate faster, right? It just means that we can tell people faster about it, even though the next block might take 3 capital delta. OK, any questions about these properties? Yes?
So then just to confirm, is this little delta actually measurable?
Yeah.
I mean,
Yeah, so just to,
know what it is?
So, it's a property of the protocol. So no. So when you write your code, right? So your code will have, you will see in a second, it'll have hard-coded capital delta, right? So you will have to protect yourself against hard-code capital delta. But you want your performance to depend on the network. So this is what typically is called network speed, right? So if your network is kind of more optimistic than your worst-case assumptions about partial synchrony, then you want to get better performance. OK, so we are going to kind of, again, formalize these properties a little bit more. So here they are. This is the inner simplex for view V. This is the certificate. So this is the value in view W for some value Z. And that's just going to be N-F votes for Z in view W. OK, that's just the notation. And again, what we want to say is that eventually you see a certificate. And that certificate can be either for a value or for bottom. The validity property is that, after GST, if you have an honest leader, then in 3 delta, everybody has a commit certificate. So I didn't tell you how the commit certificate looks, but soon we will. And the third property we want here is kind of this property, which says, this is the important safety property, which is if there is a commit certificate in this view, then the only certificate that exists for this view is a value certificate for that same value. Let me say that again. If there is a decision, a commit certificate for a value x in view W, then the adversary or you cannot create any certificate other than the value certificate for the value x. So you cannot create a different value, and you cannot create a certificate for a bottom. Make sense, these 3 properties? Yes?
Can you explain where did you get the 3 delta
The three, I will.
Question is, you mentioned 3 delta, so where is the 3 coming from? Is that related to 3 base to the mid protocol?
Yeah, there's a lower bound that says that maybe I'll get to it later, but basically if you have less than 5f minus 1, so if the number of malicious parties is more than 1/5, the best you can do is 3 delta. So there's a lower bound. Okay. Yeah, so this is kind of the best you can hope for with this property. We will talk later, and Andy will talk about getting 2 delta, good case, but then you have to go to like 5f plus 1. Okay, this is like 3f plus 1. Other questions? Good. So we're gonna implement this. Just a few comments. Sorry. Yeah. So first of all, notice that like after GST, everybody leaves the view in a 1 delta gap, right? Because if I have a certificate, I'll send it to everybody else, and so everybody leaves, right? That's kind of one observation. The other observation is that you could have multiple certificates in the same view, so you could see multiple certificates. It's only in this case, if there's a decision certificate, that there's only one, but otherwise you might see multiple ones during the protocol. And I want to say the other thing is like, what if you see a value certificate for some value x? And what does that imply? Suppose you see a value certificate for x. You know, right, that if there was a decision certificate, it had to be for x as well. Right? This is kind of the important property that you get from the safety property. And similarly, if you have a bottom certificate, you know there could not have been a decision in this round, in this view. Right? Because if there was a decision in this view, then safety would say that there could not be a skip certificate. Make sense? So these two properties just follow immediately from the safety property.
Sorry, I might have missed this. What's the difference between the commit certificate and the value?
Yeah, so I didn't tell you how a commit certificate looks like for now, but a value certificate is just MISF votes.
Sure.
Yeah.
And what's the entrance gap?
The entrance gap is the gap in time between when we start view W. Right? So it could be that maybe you start view W at time 7 and I started at time 7 plus delta. Right? So the gap between all the honest parties' entrance is no more than 1 delta. And this would be important. I mean, so yeah, we need this for validity. I guess the point is that like it's almost automatic to get this because you exit in 1 delta. So that means you probably enter in 1 delta. But it is a property to have, and if you don't have it, then yes.
Regarding some of inspirations in the protocol, can I say that this 1 certificate per view is inspired by alt stuff, and the vote for bottom is inspired by Tendermint?
No, I would say all protocols have a value certificate. That's kind of what I will definitely compare Tendermint and hot stuff to this protocol. I would say both of them don't explicitly have a skip certificate, and both of them are not dense in the sense that sometimes, at least in Tendermint or in hot stuff, you time out and you don't have a certificate. Okay.
But in Tendermint, you had always to receive them as votes, right?
Yeah, maybe in some versions, yeah. So maybe some versions do have this property. I will, depending on the amount of time I have, I have like a really nice thing to show you about Tendermint and Simplex playing together. So yes, I promise you that. Yes.
So you're saying that the timeout is not equivalent to the. You're saying the timeout is not equivalent to n-f votes for bottom?
Timeout. No, we will now build. Okay, we will build the protocol right now, and get a timeout. But where do you see timeout here?
No, you said other protocols have timeouts. Right.
Oh wait, I'm saying other protocols, when they leave a view, they don't necessarily have a certificate for the view they left.
But that's what you're using the bottom.
Simplex does. Yeah, Simplex does do it. Other protocols might not. Yeah, so I think that's kind of a small difference. This is kind of interesting if you know the other ones. If you don't know them, then it doesn't help, right?
I mean, I kind of do, but
okay.
My question is, so somehow you're using this bottom to handle that timeout case.
Yes, yes. Let's do it. We're going to implement these 3 things right now. So this is it, 4 lines. Okay. So again, I hope that by now you like think about how do I implement this. Okay. Suppose you want to implement this, right? And I only give you like 4 lines of code, right? Maybe 5. But that's it. Like so it's very simple. It's like a homework exercise that you can give to a course in distributed computing. After like the first hour, they understand the model, the basics. They can, here's 3 properties. Go ahead and try to implement this. And essentially, yeah. So I guess now I'm going to tell you what a commit certificate is. But so these are going to be these 2 certificates definitions, and then we're going to have 4 lines, okay, to implement these 3 properties. So again, let's go over the protocol. So a certificate for a value is just n-f votes, right? That you remember that. A decision certificate, a commit certificate, is just n-f final messages. So we're going to have another message called final. And we're going to assume that everybody enters, in 1 delta from each other. OK, and this is the protocol, right? I mean, and the protocol, basically, the 2 first lines are like completely obvious. There's no other choice. There's nothing you can do, right? When you start the view, you start a timer. And the second thing you do, if you're the proposer, you propose something, right? So first line is like, there's not even a choice of what to do. Second line, there's also no choice, right? If you see a proposal and it's valid, you vote for it, right? So again, no logic. So the only thing that might be happening is these next 2 lines, okay? But again, let's just look at the first line is you start the view, and if you're the leader, you propose. And the second line is if you receive a proposal, you just vote for it. Yeah, if you receive 2 proposals, you just vote for 1, right? You don't want to vote for 2 different things, of course. OK, so now this is kind of the main thing that you do is if you have a certificate, right? Having a certificate means seeing a lot of votes, right? So if you see n-f votes, you basically decide to exit the view. OK, so again, this is the dense protocol idea. Once you have a certificate, you leave the view. But before you leave the view, you also do one last thing. OK, what's the one last thing that you do? You look at your timer. If your timer is less than 3 delta, then you also send a final. That's it. If the timer is after 3 delta, you don't send the final, but you leave the view. Make sense?
Forwarding is rebroadcasting, right?
Yeah, sorry?
Forwarding.
Yeah, so yeah, forward and send, these are all going to be, all going to be sending to everybody. Yes?
So you have ON cubic.
Sorry?
You have an ON cubic communication step.
N square messages. Yeah, this whole yeah, N square messages. Yes. Yep. Yeah, unlike say linear protocols. You're right. Finally, 4th rule, right? That's the last one. Is what happens if you reach 3 delta and you did not send the final. Okay, so if you reach 3 delta and you did not send the final, then you send a vote for bottom. Yes, Alberto.
So can you give a quick intuition of why you cannot send votes for bottom upon 1 or 2 delta?
Yes. So the intuition is that we will see a better protocol for this, where you send after 2 delta, not 1. So yeah, after 1, you don't want to send after 1 because the gap is 1, so you might miss the leader. So this protocol is pretty good, and we'll get a better one. But this is Simplex. Okay?
Got it.
Yes. And now we're going to prove the properties. Okay, remember, these are the properties. 3 properties: liveness, validity, safety. And this is the protocol. 4 lines. Okay? So are we ready? Let's prove liveness. You eventually see a certificate. Why is that true that you eventually see a certificate? Well, there's 2 cases, right? Either you see a certificate, and then you forward it, then everybody sees it. Right? So if one honest sees a certificate, we're done. What's the other case? No honest party sees a certificate. If no honest party sees a certificate, right, or sends a final, sorry, they all send bottom. What happens if they all send bottom? We see a bottom certificate. Right? So liveness is kind of obvious. 2 different simple cases. Make sense? Good. What about validity? So if the leader is honest, what happens? Well, if the leader is honest, then we all vote for it. We all see a value certificate, and we all send final. And the only thing we need to check is this 3 delta rule, right? And why is it 3 delta? Well, because in the worst case, if we started together, in the worst case, I would see the certificate after 2 delta. Right? It takes 1 delta for the proposed to arrive, and then 1 delta for all the votes to arrive. But the problem is that we have a 1 delta gap. So since we have a 1 delta gap, we have to take like a 3 delta delay. So really what you are seeing, this 3 delta is like 2 delta plus the 1 delta gap delay. Make sense? So this is kind of why we have the validity. And finally, we want to say that we have safety. If there's a decision, nothing else can exist other than the value certificate. Why is that true? This is where the pigeons come to the hole.
It's even invalid SSL.
Sorry?
The term valid proposal is the key here.
Yes. Yeah. So we want to prove that exactly. So we want to prove that we have safety, right? So if there's a decision certificate, what does that mean that there's a decision certificate? Well, the definition of a decision certificate, commit certificate, is that there's n-f finals. If there's n-f finals, right, it means there's at least f+1 honest parties that send final. Okay? So there's at least f+1 honest that sent final. If there's n-f that sent final, right, then basically we know that they voted for this value, and so there could be no other certificate of promise. Good. So this is kind of we're basically 80% done in Simplex. We have a protocol. We have 4 lines plus these 2 definitions, and we have these 3 properties. And so the only thing we want to see is whether we're just completely done by just running this protocol one view after the other. Okay? And so obviously we have liveness because eventually we'll reach a view which is after GST, and we'll reach a view after GST which has an honest leader. And the gap will be no more than 1 delta, and so we'll kind of, at that point, we'll definitely have a commit certificate. So this is kind of going back to the eventual property of the consensus. Okay, validity. So again, if you look at the way we're voting, we're only voting on valid values, and so we're getting kind of only commit certificates that have values that are signed by a client. And finally, the problem is safety, right? So at least this naive version, where we're just running this protocol one after the other without looking at anything, isn't safe, right? And the reason it's not safe is because maybe in the first view somebody has a commit certificate for X, but then the next view, and because of asynchrony, there's only one party that has this commit certificate. And then in the next view, some malicious leader is kind of proposing a different value, Y. And so this is the core problem we want to prevent. We want to prevent a malicious leader from proposing a value Y, even though there was a commit certificate for X. Okay, so this is the only thing we want to kind of prevent. And so the way we're going to prevent this is by making sure that when we vote for Y, we're guaranteed that this vote is a safe vote. Okay, what does it mean to have a safe vote? A safe vote is a vote where I know that I'm voting for Y, and it's okay because if there is a decision, then only Y could have been the decision value. Okay, so this is the core problem that every consensus protocol needs to deal with, is basically to make sure that when I'm voting only for safe votes. And this is kind of where Simplex, again, diverges from other protocols about how they do this rule. Okay, so here's how we're going to do this. And basically this rule, so we had 80% of the protocol done. This is the last 20%. So this kind of safety rule gives us the final part of the protocol that was missed for Simplex. And what does this rule say? Well, it basically says that you're allowed to vote for a proposal under 2 conditions, roughly speaking. One is that, so let's just kind of unpack this. So we're in view V. We're getting a proposal for a value X. And the proposer is pointing us to an earlier view W. So this earlier view W is going to be this justification for voting X. And then there's 2 cases. So maybe one case is that all these values before it, all the views before it have a skip certificate. And the other is that I'm actually giving you some value certificate from a view W, and then all the skip certificates between W and V are skips. Okay, so these are the 2 cases. Just to make sure, through examples, if we're at view 10 and the proposer is giving you a value certificate for some value in view 9, that's okay, right? There's no skips in between 9 and 10. That's fine. Another option is that it gives you a value certificate for view 8 and a skip certificate for 9, or for 7 and then 2 skips for 8 and 9, or skips for everything. All of these are okay. And here's things that are not okay, right? If he's asking you to vote for X, but he's giving you a certificate for Y, or the only certificate you have for Y, then you will not vote. And similarly here, right? If you're in this case. So makes sense? Does the rule make sense? Good. So now with this rule, we will prove safety. Yes.
Okay, so but why are we voting for the same thing in all of these?
Oh, because we're doing a single shot protocol. Remember, all we need to do is like fix one block. Now it could be that there was a decision certificate in view number 1, but nobody knows about it, right? Because of asynchrony. So now we're going to view number 2, and we're still going to do a decision. And we'll see in 2 slides that this basically extends to a chain as well. Yeah. Yes.
So when you say U, there exists a one, and this one U, because the first time you mentioned U, right?
Yeah, all these views in between W and V. All of them. All. All views in between. All of them have to be skips. That's the rule.
Yeah, on that. These schemes are going to be a certificate for accident.
Then you start from there. There's no need to show me.
Yeah, but if the proposal.
Yeah. I try to be as simple as possible. Yeah, I mean, then you should show me a later thing, right? Don't need to show me this whole history. Yeah, but you're right. Yeah, of course. Yeah. Okay, so so now let's prove safety, and we're done, right? This is it. So what do we want to prove by safety? This is safety of the consensus protocol, right? Again, we had liveness and we had validity. We just need to prove safety of the consensus protocol. And what we want to say is this property. And before we prove it, again, this is going to be just 2 cases. Very simple, but I just want to make sure that you understand why if we prove this, we get safety. So safety basically means that there's no 2 decision certificates with different values. Okay? And why don't we have 2 different certificates with the same values? Well, this is what we're going to prove. We're going to prove, let's look at the first view with a decision certificate. And any later view, any value certificate has to be the same value, or bottom. Okay, that will imply that you cannot create another decision certificate, because decision certificates need value certificates, right? So this is kind of the safety argument that we want to prove. And this is kind of the proof. It's essentially one observation and then kind of one induction hypothesis. So the base case, what's the base case? Well, we're going to use the safety of the inner protocol. And what is the safety of the inner protocol? It says if there's a decision certificate in view V, that means there's no other certificate available other than the certificate of a value for that value in view V. Okay, so there's no bottom certificates and no certificates for other values Y. Okay, and so given this, right, imagine that somebody, a proposer, is asking you to propose, to vote for a proposal, and this proposal has some certificate from W, from some view W. So first I claim that it cannot provide a W that's older than this view V. Because it had to then show a skip certificate for view V. This is kind of why I'm using this simplified rule. So this will definitely fail, and you will not vote for it. So the only thing you might be able to vote for is something whose W is at least as large as V. Okay, and now we're just going to do a simple induction, right? If we're in V plus 1, then the only thing after V has to be this decision for this value Z. And again, like we can just show every view after view that this is essentially the same decision. Okay, so that's kind of the safety proof. Again, we're basically using the inner protocol safety for the base case, and then running kind of a simple induction argument. And just using this kind of rule for safety, for safe votes. And for those of you who are worried, well, this is just a single shot and I care about building a chain, so here's exactly the same protocol, exactly the same inner protocol, right? So we didn't change the inner protocol. We're just changing this safe voting to a safe voting that kind of works on a chain. So here, when we get a proposal, again, this proposal is in view V. It's for a chain that has all this prefix C, and then we're adding a new block B. And then we're giving an indication of where to look at the proof in view W. Okay, and now the rule is going to be very simple. We want to see that in view W, there is actually a value certificate for this chain C. And this block B is a valid block that can be extends this chain C. And just like previously, now that we have in W a value certificate, all the views U in between W and V, the current view, are skip certificates. Okay, so exactly the same rule, just for a chain. And exactly the same safety proof. Again, we look at the first commit certificate for this chain, and what we show is that any later view, any value has to contain a chain that is a prefix of this chain that we just had decision on. Exactly the same logic. For people who like a more pictorial view of this, here is kind of the pictorial view. So suppose that there's a commit certificate for a chain C in view V. That means that everybody has only a value certificate for C. OK, if everybody has only a value certificate for C, then what are the things I can vote for? Right? I can't vote for anything that comes from a view previous to V, because that would mean that there's a skip certificate for view V, but there is none. So the only valid thing that I can vote for is a chain that has C and maybe some new block B1. Okay, that means if that's the only thing I can vote for, then the outcome of view V plus 1 can either be a certificate for C and B1, or just a skip certificate. These are the only two options for view. And then you just continue kind of recursively. OK, if these are the two options, right, what is the option for view V plus 2? So again, in view V plus 2, if these are the only possible certificates, then I will not vote for anything previous to view V, because that will require to show a skip certificate in view V. But in view V plus 2, I might vote for something that has a value for C and a skip for V1. Right? Or if I have this value for C and B1, I might extend it with B2. OK, so these are the two cases, and then you can just kind of continue pictorially around this. Is the safety proof clear? Yes?
Yeah, I think it's pretty obvious that you can have only one of the three if you each, right?
Yes. Yep.
So I think it's a
Yes. Yeah, so basically, here is the whole protocol in one slide, and this is kind of what even if the next part of my talk is going to be more vague, I want you to remember this. This is kind of Simplex in one slide. Remember, we had these 4 rules for the inner protocol. We had what does it mean to be a decision, and then there was this outer protocol, which basically told us how to make sure that our votes are safe across views. Okay, so these three kind of rules give us the inner protocol of Simplex. And the reason I'm insisting on this separation is because what you'll see now is that we're going to replace sometimes the inner protocol and sometimes the outer protocol. We've already replaced the outer protocol between a single shot and a chain version, but we're going to do more of these types of changes. So you're going to see that by kind of modularizing this protocol, we can have a lot of different types of variants. OK, makes sense? Any questions, comments about Simplex? Yes?
I think it's pretty obvious, but maybe can you just walk through a case where even the first view is malicious? Is that even possible?
Yeah, it is. It is. Yeah, I'm hiding. Yeah. I don't want to go into too much. I'll just say that I'm hiding here. This one. So X needs to be valid. So when the first view is malicious, then we're only going to vote if it's valid, and so that kind of validity.
It's valid if the first one is malicious, though.
Oh, the proposal value. Yeah, so I'm assuming external validity is, yeah. So this definition is that client commands are signed, right? So there is a way for me to check that this is a valid transaction. Make sense? You're absolutely right. Yeah, and this kind of is hidden in the chain version, because in the chain version you kind of assume you have a genesis that's already well defined. Okay, so I'm going to quickly say why this is kind of the theoretical advantage of Simplex, which is that the worst case view is only 3 capital delta plus 1 small delta. And again, capital delta is this worst case bound for the global the GST time, and this small delta is going to be the network delay. And again, the analysis is going to be very simple, right? So either one party sent a final, and if a party sent a final, here I have a pictorial view of this. If one party sends a final, it has to send it before t plus 3 delta. And so everybody leaves the view in 3 delta plus 1 small delta, right, when this certificate arrives. The other case is that basically no honest party sends a certificate. If no honest party sends a certificate, it means that by time t plus 3 delta, every honest party's timer expires. Since every honest party's timer expires, they all send a skip vote, a vote for bottom. And so now you'll, at time 3 delta plus 1 small delta, everybody will see a skip certificate. Make sense? Good. So this is kind of this 3 delta plus 1 delta. And now I want to kind of go back to Alberto's point, which is, is this the best we can do, right? And does it sound like the right thing? And I want to kind of offer this additional protocol that kind of goes through what Alberto was suggesting, which is, well, let's actually make sure that we change the protocol to send a negative vote, not in 3 delta, but in 2 delta. Okay? And so this is going to complicate our life a little bit, because it could be that we're sending a negative vote, but there still is a value certificate or a decision and so on. So we're going to have to kind of deal with that. And so because of that, we're going to have six lines instead of 4 lines of the protocol. So what is the 2 first lines? The 2 first lines don't change. There's nothing smart to do about them, right? You start the protocol, you start a timer, the proposer proposes. What does the second line do? Well, the second line, if you see a vote, and again, it's a safe vote, you vote for it. Okay, this third line, if you know about reliable broadcast in asynchrony, should be very familiar to you. This is this boosting line that says that if you see t plus 1 votes for some value y, you also vote for it. Right? The intuition here is that if you're seeing f plus 1 votes, that means at least one honest party decided, oh, this is a good idea to vote. So if they decided to vote, you're going to vote on it as well. Okay. Note that now you might be voting for multiple values. So now we have a new type of risk. Okay, so this is similar. The beginning is similar to the previous protocol, right? So if you see a value certificate, you forward it and you exit the view, right? That's just like the previous protocol. But now the reason to send a final is slightly adjusted. So here's kind of the reason. If you see this certificate and it's not bottom, and you only send a vote for this value, not for any other value, then you send the final. Okay, so final is kind of saying, not only did I see a value certificate, but I myself never voted for anything else. This is the negative vote. We've already talked about it, right? 2 delta. And this is maybe kind of maybe the most nuanced rule that we had. It's not very complex, but it's a little bit we haven't seen something of this flavor before. Basically, what we're saying is if we see a bunch of votes that indicates that we're not in a view that has an honest leader after GST. Okay? So if we see n minus f votes such that there is no one value that has at least f plus 1. Okay? So you can think about it as the maximum of every value is at most f. Okay? That's kind of one way of thinking about it. So this is kind of a proof that we're not in a good view. Right? Because if we were in a good view, then the honest parties would have been voting. And so at most, F parties could have been doing something else, maybe voting for bottom. And so this would be kind of an indication that this view is bad. And then in this case, you would send a bottom. OK, so with these six properties, we basically want to, again, reprove the properties for Tim, we have until what time?
You have
15 minutes. OK. So I'll go a little bit faster here. So you look at these safety and liveness properties, and you try to prove, I guess, this property. And this is a good homework exercise to try to do it. Yeah, it's kind of a similar, and again, similar liveness bound. And the thing that we got as an advantage is that now we get 2 capital delta plus 2 small delta. So we kind of shifted 1 capital delta to a small delta. So we gain a small advantage. Is that a real important thing in practice? Probably not so much. If most of the time you anyways are paying 3 delta. The maybe bigger advantage of these types of protocols is that it works when the leader is silent. So sometimes you have a leader that for some reason just crashes and doesn't propose. And that may happen in practice. And so if that happens, or more often I guess than a malicious leader that's trying to delay your view as much as possible. And so again, this is kind of this nice advantage of these protocols that get 2 delta plus 1 small delta. Okay, I'll very quickly talk about these notions of when we were asked earlier, why do we need 3 delta? Why couldn't we get better latency, better good case latency? And by the way, this is like, I'm not aware of really like a lower bound proving that like 2 capital delta plus 2 small delta is the best to do. So yeah, I think it might be interesting to even somehow state something around that. And I guess my point is, well, you can actually get better than 3 delta good case. You can get 2 delta, right, as people happen. But then you have to pay for the fact that the number of failures is not so large. So basically, roughly one fifth, right, a little bit less than that. And yeah, please come to Andy's talk, and he will talk a lot about this. And you can kind of do similar approaches. So you can decompose this into an outer and internal protocol, and you can get kind of better latency. And again, here there's even these nuances where getting the worst case latency might require you either large messages or snarps. So again, it's an interesting kind of a challenge here to actually get like a worst case latency of 2 delta plus 1 small delta and not pay any one of these higher prices. And once you have kind of a good case for 3 delta and a fast case for 2 delta, and the natural next thing to do is say, well, maybe we can mix them together. Right? That's kind of the natural next thing to do. And this is what I call these peacetime, wartime protocols. Right? So these are protocols where you basically want to have very good performance when you're not under attack. Right? So let's say when there's only P, when P is a small number, faulty parties, then you actually get a 2 delta. So you get a very fast latency. Or if you're kind of under attack and there's F faulty parties, then you get still this 3 delta. And so again, you can do this. And again, the fact that you have a decomposable protocol means that you just take the inner protocol for the fast one and the inner protocol for the slow one, and you can combine them together. And you have this kind of one inner protocol. You combine that with an outer protocol, and things work. And of course, Roger will talk a lot more about that. OK, I'll move to the next topic, which is kind of challenges with Simplex. And I guess kind of comparing the Simplex approach to kind of what PBFT and Tendermint and hot stuff and Simplex does. I think going back to your question. So I guess this is kind of 3 or 4 ways for which you verify that the vote is safe. So the PBFT approach for verifying that a vote is safe is simply showing you a vector of locks and showing you that you're voting on the highest view lock. Right? This is very nice. The Tendermint approach is basically saying, I'm just going to give you one lock, and you're going to vote on it if your lock is at least as large as that. Hot stuff did a modification of that and said, well, actually, if you show me a key certificate that's at least as large as your lock certificate, you can vote for it. And Simplex is kind of saying something different. It's saying, I'll give you a value certificate and skips in between. Again, I'd like to kind of compare and contrast these approaches. In particular, PBFT is my first love. So for sure, it's like a wonderful protocol. And I want to say that in practice, in the normal case, right, this worry of having a large view change message or whatever should not happen. Just like all these other protocols, you can optimize that away pretty easily. And yeah, in the worst case, if you're under like extreme attack and you have a malicious leader that's trying to equivocate you in some crazy ways, and this leader doesn't care about being slashed and so on, then it can cause a large message, or if you want, you can snark it. And I want to say that in a world where people will look at these post-quantum techniques and use a lot of snarks, then this might actually not be a bad idea. But I'm going to put this here and say PBFT is wonderful, and it works quite well in the regular or normal case, right? And sure, in kind of an extreme attack mode, you might have to send a larger message. To contrast that, the challenge with Simplex is that, sure, again, the normal case is essentially constant, right? In the normal case, you probably would either, let's say, miss 2 or 3 views, right? Maybe 5 views, so you send 5 skips. It should be a very small amount of messages that you're sending. But again, in the worst case, your storage is unbounded. And anybody who's actually implemented the system knows that when the theory says it's unbounded, now you have to, when you write your code, you actually have to do something about that, right? There's no unbounded, so you have to fix something, and then, well, what if it's larger than that? Then there's a problem, and so you want to try to minimize those types of challenges, and this is kind of a little bit of a problem here of kind of handling unbounded storage. You might need to resend certificates because you lost them, and this goes back to these problems of partial synchrony. Again, people asked earlier, what happens if before global civilization time messages get lost? So I might not even see the certificates. I need to ask other people to give me their certificates. And so that might mean that I need a large amount of messages, again, in the worst case. Yes? Yeah, that's a really good idea. So you're saying you could store one certificate for all the views. You can kind of compress it. Yeah. So I guess I will take what you said as here's a very efficient and practical way to snark some cases. Yes. Yeah. No. But you're absolutely right. Like, I guess my worry here is less about. It's like maybe I'm missing some of these skip certificates, right? So, yeah. So I might need to, and maybe the skips that you have are different than the proposal. So you have to give me a certain certificate for a certain number of them. But you're right. Like I'm not saying this is if you run an implementation, you always have to. There is a corner case that will become unbounded, and then the question is how do you want to deal with it? Basically, say it will never happen, and hope for the good. But you're absolutely right. There are very good case. I guess this is kind of my point here to make it.
It's very good because you can also just
Yeah. I absolutely agree. And as somebody who's actually done this before, you can optimize the hell here as well, right? So just so you know, anytime the theory says it's horrible, in practice you look at the case and try to optimize all the good cases. But anyway, we want to at least show I like to kind of highlight some of the challenges just to make sure that we kind of understand the trade-off between them. So here's I guess Tendermint, and it has this hidden lock problem. And again, in some cases it's not a problem, especially if you have kind of a fixed view schedule or if you're waiting enough. But the core problem is basically that there's a leader in view k+1 that did not see a certificate in view k. And somebody has a certificate in view k, and you're the leader of k+1 and you did not see the certificate. And at least in Tendermint, if you propose something that's different than what I'm locked at, I will not vote for you. And so the system will get stuck in some sense. Or at least, again, in the worst case, will get stuck. So this is kind of the hidden lock problem in Tendermint. And over the years, there have been many different solutions for it. One solution is simply just wait enough time. I guess this is what kind of Hot Stuff 2 says. We'll optimize the hell of all the cases. And there's one extreme case we have to wait a little bit of time. So wait enough time so that this lock will arrive also to the leader. Leader will know what to do, and it will propose this lock. And there's kind of other approaches, and I want to say what Simplex is doing is actually offering a new, interesting way to solve this problem. It's saying, I'm the leader of view k+1. I don't have a value certificate for k, but since it's a dense protocol, I have a skip certificate. So I'll show you the skip certificate, and that will unlock you. Right? Even if you have a lock for k, the skip certificate is a proof that there was no commit in view k, so you can kind of just ignore your lock. Okay, so this is kind of the Simplex idea, and this is basically what this protocol called Complex does. Yes.
Yes, I have a question. Okay, so one of the biggest posts analyzed Simplex under party security. Is there, do you think there exists a path to an async version of Simplex, or does the Google commit rules fundamentally
The asynchronous Simplex is in a slide that I won't get into, depending on how much I. But yes, there is an asynchronous version of Simplex, and it just like in Tendermint, it saves latency. It saves a round in asynchronous communication. Okay. So this complex idea is basically saying let's kind of deal with this hidden lock problem of Tendermint. So let's basically run Tendermint and just fix it by fixing the last round. Oops. And here's kind of the idea. We're going to mix Tendermint and Simplex. And the way we're going to do it is we're basically going to run Tendermint for all the views less than k-1. So we don't need all these skip certificates. We just need to be locked or unlocked. And then just for view k-1, just for the previous view, we'll use the Simplex idea. And so now you just store your two highest locks. Why two highest locks? Because the highest one might be unlocked from Simplex, and then I'm going to use the next highest one. Okay. And so this is like your constant storage. And again, this is a very simple change to Simplex, right? Which kind of removes the bounded storage that you need in the worst case. But there's other types of advantages to this approach, right? And this is kind of maybe you get easier accountability. It's easier to kind of measure if you misbehaved. And again, everything. This protocol can actually be adapted to all the other protocols that you've seen. So all the different protocols that are Simplex-like, you can kind of mix them with Tendermint to kind of remove these problems of large change of script certificates.
From your professional knowledge, we are thinking against true boxes to have a single value. So all the state can be simplified to a single certificate. Do you think that's possible or not?
I would say different systems need different optimizations. So I don't think there's going to be a one Uber consensus protocol. I guess this is an example of basically not saying, oh, I belong to one camp or the other camp. You can take good ideas from either one, and in fact, you're only changing kind of the outer protocol. The inner protocol remains the same inner protocol that we've just seen. We just changed the outer protocol here. So again, I'm showing you kind of the advantage of modularity. Okay, so so in the few more minutes, I'm just going to flash a few more things you can do with Simplex. And so one of them is basically people are now interested a lot more in information theoretic protocols, basically protocols where you just assume you have an authenticated channel. Again, this is really nice in this kind of world where maybe you're worried about post-quantum cryptography and cryptography seems very expensive. And so you want to minimize the use of cryptography. This was the same reason that PBFT did not use cryptography as much as it could. And so these information theoretic variants basically get the same type of properties like Simplex, but they have some additional latency overhead. So in particular here, there's like one more small delta, right? Remember, we got 3 + 1. Now here we get 3 + 2. So I guess this is currently the best that we know. Maybe we can do better than that. And the way you kind of approach this is you basically say, well, I know how the outer protocol looks like, right? It's just checking that there's a skip certificate and a value certificate here and relative to this view. And now I just have to, I've seen these 3 properties of the inner protocol. I'm just going to use information theoretic techniques to implement these 3 properties. Okay, you try a little bit and you realize, well, these 3 properties are maybe a little bit too stringent. So you do a little bit of, a little bit of relaxation to them. And you get something that you can implement, again, using basically reliable broadcast techniques, right? Information theoretic techniques. And you can basically get the same variant of Simplex just using no signatures. What about synchronous protocols? So we talked a lot about partial synchrony, but actually I think there's going to be a resurgence of interest in protocols that work in synchrony. Protocols that work in synchrony are nice because your costs is much smaller, right? You actually get 2f + 1. So for the same amount of validators, you can deal with a lot more Byzantine failures. And obviously, you need synchronous network in order for this to work. And there's kind of this thesis that partial synchrony maybe was like a really good idea in the 80s and 90s of the last century, but maybe today networks are much more reliable and much more synchronous looking, using fiber optics and so on. And direct connections that maybe we should look at synchronous protocols. So anyway, you can kind of take again the same paradigm of having a dense protocol that always outputs a certificate and apply it to the synchronous model. And you can get kind of, this is, I guess I'm flashing one result that you'll see in Kartik's talk, hopefully. But again, so there's a worst case view. And here it's a little bit larger. So it's 5 capital delta + 1 delta. Maybe you can do better. And this kind of protocol has, the peacetime, wartime option. So if everybody's voting, you get 2 delta. If there's very few malicious parties, you get 3 delta. And then even if there's like the full Mountie of F people trying to attack you, you still get a commit that's synchronous, right? So this is kind of the mixture of it. And again, the way you think about this is you kind of understand the outer protocol and you try to implement the inner protocol in a synchronous model. Yeah, finally, since you asked about asynchronous Simplex, so again here, you can kind of use these Simplex ideas in theoretical algorithms for asynchrony to reduce the expected latency of a view. And again, people here who care about, I guess, the more theoretical asynchronous protocols, this is kind of nice. And again, shows you that this idea of having a dense protocol is worthwhile, not just in partial synchrony. It's also interesting and helpful in synchrony and in asynchronous. Okay, so this is kind of what I wanted to talk about, and maybe we can move to Q&A or just to relax and have some coffee. But I guess my main point is that I want you to kind of think about Simplex as a decomposable protocol that has two parts. One part that basically deals with per view, what's happening inside of you, and the other part that basically gives you a voting rule that tells you when is a safe voting, and that's a cross view. And then once you kind of see this, you can optimize each part separately, right? If you need a better latency, or if you need some better worst case guarantees, or if you need to do a change version versus a single shot version, then you can change and mix and match them. I also talked a little bit about kind of the challenges of Simplex and the worst case need for unbounded storage, and some ways to improve it, and talked a little bit about how to extend the Simplex ideas to other domains. Yeah, and there's a Decentralized Thoughts Simplex chapter that I hope to get a lot of comments from all of you about how I can improve it. Thank you. Yes.
Thank you so much. I was just hoping they could give you a little more, like to your general background. This is your main area of research, so I'm curious about that.
Yeah, I guess I really enjoy doing research in distributed computing and algorithms, and I fell in love in consensus protocols, right? Because of this like really nice connection, and because it's kind of a gift that keeps on giving, and you continue to have new interesting ideas here. So I will say, yeah, there's a lot more things in consensus going on than just simplex variants, but I really like this simplex prism of things, because for me, looking at a problem that I thought about for a long time through a new prism gives me new insights. Right, so that's kind of why I'm excited about that.
Thank you so much.
Sorry, I have a single question about Simplex for me is account level. So by voting for a value, then voting for what value, or voting for a value, then voting for another value, you're doing something in the total calculation. And this is logical, this is a problem. So how we handle those is different. So always separate correct process that is for value and for new, and a positive process that will for some values
Yeah, this is a really good question, and and Joachim is going to talk a whole session about accountability. I will say that there are challenges with simplex and accountability. Basically, you need to record the reason why you voted, and yeah, this recording needs to be able to. We need to be able to show it to a court, right? This is kind of why, again, notwithstanding the fact that you can optimize these things, if you want accountability, this complex idea for me helps that. So it removes some of that aspects. But yeah, I would say, I don't know, where's Neil? Yeah, like we know how to do accountability, but it's still kind of an open question about what's the best way of doing it with simplex. Or what would you say? No? Okay. Yeah, Joachim is going to talk about it. So yeah, for sure. We want the recording. Yeah, this is a good question, and I would say the following. Most of these protocols have this 3-round propose, vote, final. And so usually, we think about these as basically one authenticator in each one of these phases. So there's no, I guess, main big difference between these protocols as long as you're looking at like n-square communication. The place where you might want to try to optimize, and there's two ways to optimize, right, is if you really are worried about paying n-squared communication for a consensus round. I will say that I think that for like several hundreds of validators, I think this n-square message communication is pretty reasonable and pretty practical. So I don't think that is our current bottleneck. I do believe that if you want to move to like a larger setting of, let's say, tens of thousands of validators, then this n-square becomes kind of more prohibitive. And there's two approaches to do that, right? One is to look at these linear protocols, and Simplex is definitely not one of them, right? This is more the hot stuff type protocol. Or you subsample. This goes back to the Algorand approach. Now, can you subsample and run like a subsample Simplex or a subsample PBFT? Yes. But I believe that space is, maybe it's going to be the 5th generation. But I think we're still not at the point where we need extremely low latency that is below the n-square bottleneck of the amount of validators we have. That means there are systems with hundreds of validators that have very good latency, and there are systems with tens of thousands of validators that are currently happy with the latency they have. So to the extent that you really wanted to get lower latency and many, many validators, there are techniques to do that. I don't think we're seeing them in practice yet. And if I had to guess, you would use subsampling, and then in that subsampling, you would probably use one of these protocols like Simplex. Yes, subscription, yes.
This is that lead to 3 again, and the value forms the value relationship also
Yeah, because the way you should think about this is that I'm showing you a skip certificate, and that means that the previous thing didn't increase the chain, but here's what I'm suggesting to increase the chain. So you're still pushing your own, so don't think about a skip certificate as like committing nothing. Especially if you're building a chain protocol, you're saying here's a skip certificate and here's what I want to add to the chain. So I'm basically just deciding, to which chain to add to. So you still get your 3 delta. Oh, yeah.
All right, let's make it time.